A single electron leaves a heated metal plate and moves toward a barrier containing two slits cut into a sheet, thinner than a human hair. Behind that barrier sits a detector screen glowing faint green in the dark. The laboratory is silent, except for cooling fans and the ticking of instruments counting impacts one particle at a time. What should happen is obvious. The electron should pass through one slit or the other, like a bullet through a doorway. Instead, after thousands of electrons strike the screen, a pattern emerges that looks exactly like overlapping water waves interfering with themselves. And it gets worse. The moment physicists place a detector near the slits to observe which path the electron actually took, the interference pattern vanishes instantly. The electron stops behaving like a spread-out wave and begins behaving like a localized particle. Same apparatus, same electron gun, same room temperature. The only difference is the act of measurement itself. For nearly 100 years, humanity has repeated this experiment in universities, military laboratories, national research institutes, and superconducting quantum facilities across the planet. The result never changes. Quantum mechanics predicts the outcome with astonishing precision. 12 decimal places. Semiconductor chips work because of it. MRI machines work because of it. Lasers work because of it. The modern world rests on top of equations that have never once failed experimentally. But the meaning of those equations remains completely unresolved. Not partially unresolved, completely. The deepest problem in physics is not that we lack data. It is that the data appears to describe a reality that no one can explain in plain language without tearing apart some other part of reality in the process. And by the end of this video, you are going to see why a growing number of physicists believe the crisis is no longer confined to quantum mechanics itself. It may reach all the way down to the meaning of truth, observation, and the existence of a shared world. Because if the universe changes when it is observed, then the thing staring back at you from the darkness on your screen right now may not exist in the way you think it does. In 1801, Thomas Young performed what looked like a simple optics demonstration. He shined light through two narrow slits and projected the result onto a wall behind them. Instead of two bright bands appearing on the screen, a striped interference pattern emerged, bright regions where waves reinforced each other, dark regions where they cancelled out. The conclusion seemed unavoidable. Light behaved like a wave. For more than a century, physics built itself around that assumption. Then quantum mechanics arrived and shattered the comfort of that picture. By the 1920s, physicists discovered that electrons, objects previously understood as tiny particles of matter, produced the exact same interference pattern when fired through two slits. Not groups of electrons, individual electrons, one at a time. In 1961, Klaus Jönsson repeated the experiment with electrons in a modern laboratory setup, confirming beyond dispute that matter itself behaved wave-like under the right conditions. Later experiments pushed the result even further. Physicists sent entire molecules through double slits. In 1999, researchers at the University of Vienna demonstrated interference patterns using fullerene molecules containing 60 carbon atoms. Objects far larger than single particles still behaved as though they spread across space like waves. Imagine standing in front of a wall with two doors cut into it. You throw tennis balls one by one toward the barrier. Common sense tells you every ball must pass through the left door or the right door. Now imagine that after an hour of throwing balls, the marks on the wall behind the barrier begin forming the rippling pattern of overlapping ocean waves. Not because the balls collided with each other, they were thrown individually. The pattern forms even when only one object moves through the apparatus at a time. That is not an analogy for quantum mechanics, that is quantum mechanics. The situation becomes unbearable when measurement enters the picture. Physicists place detectors directly at the slits to determine which path the electron actually traveled. The moment the path becomes known, the interference pattern disappears. The electron suddenly behaves like an ordinary particle again. Remove the detector, and the wave pattern returns. Observe the path, and reality changes. Stop observing, and reality changes back. Niels Bohr and Werner Heisenberg understood immediately how catastrophic this was for classical physics. The equations themselves were not the problem. Schrödinger's wave equation predicted the probabilities perfectly. The crisis came from interpretation. What exactly is the electron before measurement? A physical wave? A cloud of probabilities? A hidden object with unknown properties? And what counts as a measurement in the first place? No one could answer cleanly. The Copenhagen interpretation emerged not because it solved the mystery, but because it allowed physicists to continue working despite the mystery. Bohr essentially argued that quantum mechanics does not describe objective reality itself. It describes what we can say about measurements. Before observation, the wave function evolves smoothly as a spread of possibilities. Upon measurement, it collapses into a single outcome. But Bohr never defined precisely where this collapse occurs. Neither did Heisenberg. Neither did John von Neumann, despite formalizing the mathematics in extraordinary detail. The boundary remained disturbingly vague. Imagine you are watching a coin spinning on a table. Before you stop it, you naturally assume the coin is already either heads or tails underneath the blur of motion. Quantum mechanics says no. Before measurement, the system genuinely exists in multiple possible states simultaneously. The problem is that the equations never specify what physically transforms possibility into reality. Not human eyes, specifically. Not consciousness, necessarily. Just measurement. A word sitting at the center of modern physics like a locked door nobody can open. And the deeper physicists investigated, the stranger the implications became. By the late 1920s, quantum mechanics had become the most successful predictive framework in the history of science. The equations worked with terrifying accuracy. Physicists could calculate atomic spectra, chemical bonding, radioactive decay, and the behavior of semiconductors with precision no previous theory had ever achieved. The practical success was so overwhelming that many researchers stopped asking what the equations actually meant. They focused instead on calculation, prediction, engineering, results. But a small group of physicists understood that the philosophical wound at the center of the theory had never healed. Niels Bohr, working in Copenhagen alongside Werner Heisenberg, proposed an interpretation that would dominate physics classrooms for nearly a century. According to the Copenhagen interpretation, the wave function is not a physical object in the ordinary sense. It is a mathematical description of probabilities. Before measurement, a quantum system exists in a superposition of possible states. When a measurement occurs, the wave function collapses into a single outcome. That explanation sounds manageable at first, until you ask the obvious question. What physically causes the collapse? Bohr avoided giving a direct answer. Heisenberg often spoke as though the act of observation itself played a special role, but his descriptions shifted depending on the audience and the decade. John von Neumann formalized the mathematics in 1932 and demonstrated something deeply unsettling. If measuring devices themselves obey quantum mechanics, then the chain never naturally ends. An electron interacts with a detector. The detector interacts with a scientist. The scientist interacts with photons entering their eyes. Those photons interact with neurons firing in the brain. At what exact point does possibility become reality? The equations never say. Imagine you place a cup beneath a leaking ceiling during a storm. Every second, water drips unpredictably into the cup. Now imagine that before you look at the cup, the water level does not possess a single definite height. Instead, every possible water level exists simultaneously as overlapping possibilities. Only when you observe the cup does one outcome become real. That is already strange enough. But now imagine the cup itself also exists in multiple possible states until another observer measures it. Then imagine the observer exists in multiple possible brain states as well. The instability spreads outward like a fracture in glass. Erwin Schrödinger understood how absurd this sounded, which is why he proposed his famous cat thought experiment in 1935. A cat is sealed inside a steel chamber containing a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the poison releases and the cat dies. Quantum mechanics says that before observation, the atom exists in a superposition of decayed and non-decayed states. Therefore, the entire system, including the cat, evolves into a superposition of alive and dead. Not metaphorically, literally. Schrödinger did not invent this scenario to support Copenhagen. He invented it to expose what he saw as the insanity hidden inside it. Yet generations of physicists eventually became accustomed to saying phrases like, "The cat is both alive and dead until measurement," as though repetition could dull the conceptual violence of the claim. Albert Einstein refused to accept this framework. In 1935, alongside Boris Podolsky and Nathan Rosen, he published the EPR paper, arguing that quantum mechanics must be incomplete. Einstein hated the idea that reality depended on observation. "I like to think the moon is there even if I am not looking at it," he famously remarked. To him, a physical world should possess definite properties independent of measurement. Quantum mechanics answered him with silence, and the deeper experiments went, the less escape seemed possible. In 1964, John Bell derived a theorem proving that any hidden variable theory preserving local realism would produce statistical limits that quantum mechanics violates. Beginning in the 1970s, Alain Aspect and later experimental teams tested Bell inequalities repeatedly using entangled particles separated by kilometers. Quantum mechanics won every time. The universe behaved exactly as the equations predicted, not locally, not classically, not intuitively. You could still believe reality exists independently of observation. You could still believe the wave function merely hides deeper variables beneath it. But every year, the available space for those beliefs grew smaller. And into that shrinking space stepped a young physicist named Hugh Everett, carrying an idea so extreme that even Bohr's generation recoiled from it. In 1957, a 27-year-old graduate student at Princeton looked at the collapse problem and concluded that the mistake was not in the mathematics. The mistake was in assuming collapse happens at all. His name was Hugh Everett III. Everett studied under John Wheeler, one of the most respected physicists in America, a man who had worked with both Niels Bohr and Albert Einstein. Wheeler understood immediately that Everett's idea was explosive, because instead of trying to explain what causes the wave function to collapse, Everett simply removed collapse from physics entirely. The wave function never collapses, not ever. According to Everett's interpretation, quantum mechanics evolves smoothly and deterministically at all times through Schrödinger's equation. When a measurement occurs, the observer becomes entangled with the system being observed. Different outcomes no longer collapse into one reality. They separate into distinct branches of reality that continue independently from each other. You are not watching probabilities resolve into facts. You are splitting alongside them. Imagine you are standing in a corridor with 1,000 identical doors stretching ahead into darkness. Every time a quantum event occurs, one door does not open while the others vanish. Instead, every door opens simultaneously. Behind one door, the electron spins upward. Behind another, downward. Behind one, a radioactive atom decays. Behind another, it does not. And behind each door exists a version of you who experiences only that outcome, fully convinced their reality is the only one that exists. The mathematics does not privilege any branch as more real than another. That is, many worlds. Everett's proposal solved one enormous problem immediately. There was no longer any mysterious collapse triggered by measurement, no special role for consciousness, no invisible boundary separating quantum systems from classical observers. The same equations governed everything continuously, from electrons to galaxies to human brains. But the price was almost unbearable. Reality had to branch constantly. Every interaction producing multiple quantum outcomes generated new non-communicating branches of the universe, not occasionally, constantly. Every photon scattering off dust, every radioactive decay, every molecular interaction inside your body. Reality would not merely contain many worlds somewhere far away in space. It would generate incomprehensible numbers of worlds every fraction of a second, and these worlds would all be equally real. Bohr despised the idea. So did most of the physics establishment. When Wheeler brought Everett's work to Copenhagen, hoping Bohr might engage with it seriously, the response was devastatingly cold. The Copenhagen school viewed Everett's interpretation as philosophically reckless, almost offensive. Everett revised his dissertation under pressure, softening some of the more radical language before publication. It barely mattered. The paper was largely ignored. Everett eventually abandoned academic physics altogether. He moved into military consulting and Cold War strategy work for the Pentagon, helping analyze nuclear war scenarios during the height of thermonuclear tension. Friends later described him as increasingly detached and emotionally distant. He drank heavily, smoked constantly, died of a heart attack in 1982 at only 51 years old. For decades, his interpretation survived mostly at the fringes of physics. Then something strange happened. As quantum computing advanced in the late 20th and early 21st centuries, many worlds began returning to mainstream discussion. Physicists building quantum algorithms realized the mathematics behaved astonishingly naturally under Everett's framework. David Deutsch at Oxford became one of its strongest defenders, arguing that quantum computation itself made the most sense if parallel branches genuinely existed. In his view, quantum computers worked because computations occurred across multiple branches of reality simultaneously, not metaphorically, physically. You can reject many worlds emotionally. Many physicists still do. But the interpretation possesses a brutal internal consistency that Copenhagen lacks. There is no vague collapse mechanism hiding in the shadows. No special observer hovering mysteriously outside physics. Just one universal wave function evolving relentlessly according to mathematical law. The problem is that this solution transforms reality into something almost impossible for the human mind to emotionally tolerate. Because if Everett is correct, then countless versions of you are branching away continuously as you hear this narration. Versions making different choices. Versions who died years ago. Versions who never clicked on this video at all. An immeasurable forest of parallel conscious histories, all emerging from the same underlying quantum structure. And by the early 2020s, the situation became even stranger, because physicists were no longer merely debating Copenhagen versus many worlds. The field had fractured into radically incompatible visions of reality itself. By 2025, quantum mechanics had achieved something almost absurd. It became the most experimentally successful theory ever created, while simultaneously splintering into mutually incompatible explanations of reality. Physicists were no longer arguing over minor details. They were defending entirely different universes hidden beneath the same equations, and the equations themselves refused to choose sides. One camp turned toward cubism, short for quantum Bayesianism, developed primarily by Christopher Fuchs and Rüdiger Schack. Cubism takes one of the most radical positions in modern science. The wave function does not describe objective reality at all. It describes an observer's personal expectations about future experiences. Quantum mechanics becomes less a theory about the universe itself and more a user manual for updating beliefs after interactions with the world. In cubism, the electron does not possess a hidden objective state waiting to be discovered. The wave function exists inside the observer's knowledge. Reality becomes participatory, not necessarily created by consciousness in the mystical sense, but inseparable from the experiences of agents embedded within it. Many physicists recoil from this immediately, because it sounds dangerously close to abandoning objective reality altogether. Then there is Bohmian mechanics, originally proposed by Louis de Broglie in the 1920s and later expanded by David Bohm in 1952. Bohm rejected the idea that particles exist as mere probabilities. In his interpretation, particles always possess definite positions. Always. Electrons are real localized objects moving through space along precise trajectories. The strange quantum effects emerge because particles are guided by an invisible pilot wave evolving according to Schrödinger's equation. At first glance, this sounds comforting, classical even, until you realize the pilot wave must operate non-locally, instantly, across arbitrary distances. Imagine two entangled particles separated by 1,000 kilometers, one in Geneva and one in Tokyo. In Bohmian mechanics, measuring one particle immediately influences the guiding wave affecting the other, not at light speed, immediately. Einstein called this spooky action at a distance because it appeared to violate the deepest structure of relativity itself. Yet Bell's theorem and decades of experiments increasingly forced physicists toward exactly this kind of non-locality. Reality, it seemed, might be stitched together beneath the visible surface by connections space itself cannot limit. Roger Penrose refused both Copenhagen vagueness and many worlds infinity. Alongside Hungarian physicist Lajos Diossi, he developed objective collapse theories, suggesting that wave function collapse is a genuine physical process triggered by gravity itself. According to Penrose, superpositions become unstable when differences in space-time geometry grow sufficiently large. Tiny particles can remain in quantum superposition for long periods. Larger systems cannot. Reality collapses objectively because space-time cannot tolerate indefinite coexistence between conflicting geometries. Not observation, not consciousness, gravity. Penrose even proposed rough timescales for collapse based on gravitational self-energy differences between states. Laboratories began searching for measurable signatures, ultra-cold mirrors, superconducting resonators, massive molecule interferometry experiments. So far, standard quantum mechanics still survives every test. But the search continues because objective collapse offers something physicists desperately crave, a real physical mechanism. Then Carlo Rovelli introduced relational quantum mechanics, an interpretation so philosophically strange it almost sounds fictional. Rovelli argues that physical properties exist only relative to other systems. There is no absolute state of reality independent of interactions. An electron may possess one state relative to a detector and another relative to an outside observer simultaneously, without contradiction. Not because one observer is wrong, because state itself is relational. Imagine you and another person stand on opposite sides of a mountain watching a storm. From your side, the clouds move east. From theirs, west. Both descriptions are valid relative to position. Rovelli extends this logic down into the foundations of existence itself. Reality becomes a network of relations without a single privileged global perspective hovering above it all. You can feel the fragmentation now. One interpretation says reality branches endlessly into parallel worlds. Another says the wave function reflects subjective belief. Another says hidden particles ride invisible non-local waves. Another says gravity physically collapses quantum states. Another says properties exist only relative to interactions. These are not tiny academic disagreements. These are incompatible ontologies, incompatible universes. And yet every interpretation reproduces the same experimental predictions with astonishing precision. Imagine entering 5 separate rooms. Inside each room sits a physicist calmly explaining the true nature of existence. In one room, infinite worlds split continuously. In another, reality depends on observers updating beliefs. In another, hidden variables guide particles beneath visible space. In another, space-time itself crushes quantum uncertainty into definiteness. In another, objective reality dissolves into pure relations between systems. Then imagine every single physicist can predict the outcome of experiments equally well. That is the actual state of foundational physics. You are not looking at a field that solved reality. You are looking at a civilization using equations it does not understand while arguing over what kind of universe those equations are describing. And in 2018, a thought experiment emerged that pushed this crisis to a terrifying new level, because it suggested that quantum mechanics may not merely be strange, it may be logically inconsistent, depending on who is observing whom. In 2018, Daniela Frauchiger and Renato Renner published a paper that sent a shockwave through the foundations of quantum physics. Not because it introduced a new experiment, not because it revealed unexpected data from a particle accelerator. The paper was purely theoretical, a thought experiment, just logic, mathematics, and the existing rules of quantum mechanics applied with ruthless consistency. And the conclusion was devastating. Under certain assumptions, different observers using standard quantum mechanics can arrive at contradictory facts about the same event, with both conclusions appearing internally valid, not disagreement from ignorance, not measurement error, contradictory realities generated by the theory itself. The paradox builds on an older idea proposed by physicist Eugene Wigner in 1961. Wigner imagined a scenario now called Wigner's friend, A scientist sits inside a sealed laboratory, performing a quantum measurement on a particle. Outside the lab stands Wigner himself, unable to see the result. From the perspective of the scientist inside, the measurement produces a definite outcome. The particle is observed. Reality appears resolved. But from Wigner's external perspective, the entire laboratory, including the scientist and their memory, should still evolve according to quantum superposition. Until Wigner opens the lab, the whole system exists as overlapping possibilities. One observer sees a definite fact. Another observer describes that same observer as existing in superposition. Quantum mechanics allows both descriptions simultaneously. For decades, physicists treated this as strange but manageable. Frauchiger and Renner pushed the scenario much further. They constructed a multi-observer extension involving 4 agents reasoning about each other's measurements inside nested quantum systems. The mathematics showed that if you assume 3 seemingly reasonable conditions simultaneously, standard quantum mechanics generates logical contradiction. The assumptions were simple. First, quantum mechanics applies universally, even to observers themselves. Second, measurements produce single definite outcomes. Third, different observers can consistently combine their conclusions into a shared account of reality. Frauchiger and Renner demonstrated that these assumptions cannot all remain true at the same time. One of them must break. Imagine 4 people standing in separate soundproof rooms, connected only through carefully timed messages. Each person performs measurements and reasons about what the others must have observed. Step by step, each conclusion follows logically from the equations. No one cheats, no arithmetic fails. Yet by the end, the observers derive mutually incompatible statements about what occurred, not because reality is hidden, because reality itself refuses to stabilize into one globally consistent story. The paper did not prove quantum mechanics is wrong experimentally. The equations still work beautifully. What it proved is that the meaning attached to those equations may be fundamentally unstable. Depending on the interpretation you adopt, the contradiction appears in different places. Copenhagen sacrifices universal applicability. Many worlds sacrifices single outcomes. Cubism sacrifices observer-independent facts. Relational quantum mechanics sacrifices absolute states shared across perspectives. Every escape route demands payment, and this is where the crisis planted at the beginning of this video closes its loop. Remember the electron approaching 2 slits in darkness. Remember the interference pattern vanishing under observation. For nearly a century, physicists hoped the weirdness could be quarantined inside microscopic systems, safely separated from ordinary human experience. Frauchiger and Renner shattered that comfort. Because their paradox drags the observer directly into the equations, not metaphorically, formally. You are part of the system now. If quantum mechanics applies universally, then your observations can themselves become elements inside larger quantum descriptions viewed by other observers. The clean boundary between observer and observed dissolves completely. Reality becomes layered, perspective-dependent, and potentially incompatible across levels of observation. The situation is almost impossible to emotionally absorb because human consciousness evolved for a stable world, a shared world, one sky, one history, one sequence of events experienced collectively. Quantum foundations increasingly suggest that this intuition may not survive contact with fundamental physics, and yet the equations continue working. That is the part that truly unsettles physicists. If the theory failed experimentally, the crisis would be easier. Scientists would search for corrections, build better models, move forward. But quantum mechanics succeeds too well. Every transistor in your phone, every GPS correction from relativistic timing, every laser pulse traveling through fiber optic cables, the predictions remain flawless, while the underlying reality fractures into mutually incompatible explanations. It should not happen this way. A civilization is not supposed to build its entire technological existence atop equations whose meaning remains fundamentally contested after 100 years. And yet here we are, surrounded by quantum devices, unable to answer the most basic question those devices raise. What exactly is the thing we call reality before it is observed? For 100 years, physics has existed in a state that would have horrified earlier generations of scientists. Isaac Newton could describe gravity and believe he was uncovering real mechanisms governing the cosmos. James Clerk Maxwell could write down equations for electromagnetism and assume electromagnetic fields genuinely existed in the world outside human minds. Even Einstein, despite all his revolutions, believed reality possessed an underlying structure independent of observation. Quantum mechanics broke that continuity, not experimentally, philosophically. And the longer the crisis survives, the heavier it becomes. You are living inside a civilization powered by a theory whose interpretation remains radically unresolved. The smartphone in your hand works because engineers can manipulate quantum tunneling inside semiconductors only nanometers wide. MRI scanners rely on quantum spin states aligning inside magnetic fields exceeding 1.5 Tesla. Quantum electrodynamics predicts the electron's magnetic moment correctly to roughly 1 part in a trillion, making it one of the most accurate scientific predictions ever achieved. The equations function with near supernatural precision. But beneath those equations, the ground remains unstable. Some physicists accept this pragmatically. Shut up and calculate, as the old cynical phrase goes. The mathematics predicts outcomes. Perhaps demanding deeper meaning is unnecessary human vanity. Perhaps reality simply is quantum mechanical, and our classical intuitions were never equipped to comprehend it. But the discomfort refuses to disappear because the unresolved questions are not decorative philosophical extras attached harmlessly to the side of physics. They strike directly at the meaning of existence itself. Does the moon exist with definite properties before observation? Do multiple versions of you branch endlessly through parallel worlds? Are physical properties relational rather than absolute? Does objective reality even survive quantum theory intact? These are no longer purely metaphysical questions. They emerge directly from the equations governing matter and light. Imagine waking tomorrow to discover that every map on Earth functions perfectly. Every road leads exactly where predicted. Every GPS coordinate remains accurate to within centimeters. But no one can agree whether the planet itself is round, flat, simulated, branching, observer-created, or relational. The navigation still works, the technology still functions, but the underlying reality dissolves into incompatible interpretations. That is where quantum mechanics has left modern civilization. And perhaps the strangest part is how emotionally numb we have become to this fact. You hear phrases like wave function, superposition, and quantum state so often that the conceptual violence hiding inside them begins to fade. But pause for a moment and actually feel what the theory implies. A particle can exist in overlapping states until interaction. Entangled systems remain correlated across kilometers in ways classical space-time cannot comfortably explain. Observers themselves can become part of quantum descriptions viewed externally by other observers. Shared objective reality may not exist in the clean, universal way your nervous system assumes every waking second of your life. You still wake up each morning believing the world is simply there, stable, continuous, independent of perception. Quantum mechanics has spent a century quietly undermining that confidence, and yet you cannot escape back into classical intuition because the universe keeps confirming the quantum framework experimentally, again and again, through Bell tests, through superconducting interference devices, through delayed choice experiments, through quantum teleportation protocols, through every functioning transistor and laser surrounding modern life. It should not exist. It does. It should not behave this way. It does. It should not force reality itself into interpretational crisis. But it does. Perhaps future physics will eventually reveal a deeper layer beneath quantum mechanics, the way relativity replaced Newtonian absolutes with space-time geometry. Perhaps hidden structures still wait undiscovered beneath the wave function. Or perhaps this is the final shape of reality. Not a single objective world unfolding mechanically through time, but a participatory structure, where observation, relation, probability, and existence intertwine at levels human language was never designed to describe. Because language evolved for survival on African plains, it evolved to track predators, weather, food, faces, social trust. It did not evolve to describe particles existing in superposition or observers nested within contradictory quantum descriptions. The fact that your brain resists these ideas may not mean the universe is irrational. It may simply mean the universe was never built for minds like ours to intuitively understand. And that possibility carries a peculiar loneliness. As the stars drift silently across your screen, remember this: every object you have ever touched, every atom inside your body, every neuron firing in your brain obeys quantum laws no human being fully understands. The world feels solid because decoherence buries the underlying uncertainty beneath astronomical numbers of interactions every second. But beneath that apparent solidity, the unresolved structure remains. Quiet, invisible, waiting. A century ago, physicists opened a door using mathematics and found something staring back at them from the other side. They are still arguing over what they saw. Meanwhile, the rest of us continue building our lives inside the shadow of that open door, hoping reality remains there when we look away. There is a final detail that makes this even harder to dismiss. Quantum mechanics was never intended to become a philosophy of reality. The pioneers who built it were trying to solve practical problems: blackbody radiation, atomic spectra, the stability of matter itself. Max Planck introduced energy quantization in 1900 almost reluctantly. Einstein explained the photoelectric effect in 1905 without realizing he was helping ignite a conceptual revolution. Schrödinger hoped his wave equation would restore continuity to physics, only to discover it generated superpositions that disturbed even him. The crisis emerged accidentally, as though reality revealed more of itself than the scientists intended to uncover. And once revealed, it could not be hidden again. Every decade since has deepened the fracture. The 1982 aspect experiments strengthened the reality of quantum entanglement. In 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger specifically for experiments demonstrating violations of Bell inequalities and establishing quantum information science. Not fringe speculation, not philosophical fantasy. Core physics, awarded at the highest level scientific civilization possesses. The universe keeps validating the mathematics while refusing to explain itself in ordinary human terms. You can feel the psychological tension this creates inside modern science. Publicly, physics projects confidence, precision, mastery. Particle colliders spanning 27 kilometers beneath Switzerland, space telescopes positioned 1.5 million kilometers from Earth, quantum processors operating at temperatures near 15 millikelvin, colder than interstellar space itself. The technological power is real, but beneath that confidence sits an unresolved silence. Because no equation in quantum mechanics explains why one specific outcome becomes your experienced reality rather than another. No experiment tells us whether the wave function is physically real or merely informational. No consensus exists regarding whether the universe fundamentally contains one world, infinite worlds, observer relative worlds, or something stranger than all of them combined. And the longer this uncertainty survives, the more it begins to resemble not a temporary gap in knowledge, but a permanent feature of existence itself. Maybe that is the true lesson hidden beneath a century of arguments. Perhaps reality is not obligated to organize itself into forms the human mind finds emotionally comfortable. Perhaps the desire for one clean, observer-independent story of the universe is itself a relic of evolution, useful for survival, but inadequate for fundamental truth. Quantum mechanics may not be failing to provide a simple picture because physicists are not smart enough. It may be failing because simplicity was never built into the foundation of reality to begin with. And if that is true, then every moment of certainty in your daily life rests atop structures far stranger than you can directly perceive. Right now, your brain is converting photons into electrical signals. Quantum fields vibrate beneath every atom in your body. Invisible probabilities evolve continuously beneath the appearance of solidity. The room around you feels stable because uncertainty averages itself away across trillions upon trillions of interactions. But the deeper layer never disappears. It only hides beneath scale, like waves beneath ice. And somewhere tonight, in laboratories glowing softly with detector screens and superconducting circuits, physicists are still repeating the same experiment that began this crisis generations ago. Electrons crossing barriers, interference patterns emerging in darkness, reality changing under observation exactly as the equations predict. Still unexplained, still waiting, still staring back at us from the other side of the slit.